Good afternoon, welcome back to track 2, the afternoon session 3. We've got 4 very interesting talks, very diverse talks, everything from computer vision to autonomous vehicles, and a little bit about our incubator here, technological incubator. We've got quite a tight schedule, so I'm going to invite our first speakers on very shortly. Just to remind you, if you've got any questions, do feel free to add them into the YouTube chat. And as long as there's time at the end, we'll present to the guests, to the speakers. If not, then do feel free to email them afterwards. With no further ado, I'll introduce Dr. Lyndon Smith, a colleague of mine. Welcome, Lyndon. You're here to talk to us about the new machine vision lab in our engineering facility. I'll just put your screen on as well and take myself off.
Okay. Hello everybody, my name is Lyndon Smith. I'm the Professor in Computer Simulation and Machine Vision at UWE. So what I'd like to do now today is give a little bit of a background on the new Machine Vision Lab, which of course is in the new building, which is Z Block. And it's a new state-of-the-art engineering building dedicated to teaching and research. It's a facility providing space, as it says there, to learn and explore, giving you hands-on experience of various types, and also containing a range of dedicated learning spaces. So it's a modern building, as you can see, and it's contributing to the university's vision of promoting multidisciplinary collaborative learning and supports the predicted increase in demand for skilled engineering graduates across the region. And that is quite a considerable demand because engineering is, of course, a big employer in this part of the UK, with a long tradition of aerospace and other types of engineering in Bristol. It's quite a nice design, I think, really, with a contemporary style and the modern limited corrosion panels on there. Really quite complements the other buildings, which is a business school opposite. And there's the entrance. So it's finished in November 2020, and the building supports many different engineering disciplines in one, as it says, contemporary space. Provides different and more flexible ways of working for both our students and staff, training the next generation of engineers. And the students can get into this. You can see a modern space. This is a large area atrium in the interior of the building. That's the entrance down the bottom there. And they can build up the skill sets, of course, for accessing the kit used by professional engineers in the brand new state-of-the-art facilities that are built into here. They're going to get hands-on experience with engine test cells, wind tunnels, virtual reality. There's a cell. There's a cave built into that, and of course, machine vision. Now, talking about machine vision, the new machine vision lab in this building is where the students are going to get a great facility for undertaking projects and performing research. In doing this, they get a boost in the achievements and expertise of the Centre for Machine Vision. As you know, the Centre for Machine Vision, or CMV, is located in the Bristol Robotics laboratory, the BRL, which is, of course, in T Block at the French campus. So really quite near to the new Z Block and easily within striking distance there. And the new vision, or new machine vision laboratory, or you could call it the Robot Vision Lab in this building, is being sponsored by Scorpion Vision Limited. Scorpion Vision is a British company supplying machine vision equipment to the automation industry, working with machine builders, system builders, and developing reliable solutions to all sorts of automation-related vision problems for a range of industries. This, as you can see, is their logo, and that's the sign that we're going to install in the new vision laboratory. So what I've got here is a walkthrough where we can approach. This is a VR walkthrough that was done a little while ago, some time ago, but it's actually remarkably similar to how it turned out. So we're just approaching the new engineering building here in the VR simulation. And these two up here are quite around the building quite a lot, these two characters on here. But as we approach it, sorry about the jerky way I'm doing it, because I'm not an expert in using this particular visualization, but we're just coming out the ground level for the main entrance. And as we come through these hallways and doorways, there's a lift on the right there. We're coming into the main atrium area now, and we can't really see it. Like if I turn around, we'll be able to see it, but I'm just going on, because what I want to do is go on to the main digital gallery, which is just through these doors up here. When we get through these doors of the digital gallery, there will be a staircase we'll be able to see down into what the view looks like down in the gallery itself. Now, a lot of equipment that's been installed down here makes it look a little different to how it appears in this diagram, but what we can see here is a big room, and what's been installed in this room is actually a cave, just about here as a matter of fact. But around this cave are these benches that have been installed where we want to establish these cells will comprise the Scorpion machine vision laboratory. So each cell has a slightly different aspect of machine vision which the students are able to investigate. So that's the fly through. If we just go on and think about these cells, as I've got 5 of them, and I'll just go quickly through what each of them is addressing. So the first one is the importance of lighting in machine vision. Then we move on to capabilities and benefits of 3D machine vision, and 3D being a niche which we've developed in our lab over the last 20 odd years. Then photometric stereo, which is one of the main techniques we've applied in our lab to all sorts of sectors and industries. Number 4 is polarisation in machine vision, another very important technique. And 5, AI deep learning. This is where we're letting the tiger out of the cage for machine vision. I'll explain a little bit of detail what I mean by that. And actually, here are some cameras supplied by a company called Hikvision, which it's a very large world leader in supply of cameras, and they're distributed through Scorpion Vision. All the cameras that Tesco have in their stores, for example, are made by Hikvision. So just going through each of these in a little bit of detail. The first one, investigate the importance of lighting in machine vision. Here, the students will get a chance to use illumination under computer control of various objects using a wide range of light sources. So we have different illuminants, LEDs, for example, of different wavelengths, and different types of camera, near infrared or shortwave infrared. And these different wavelengths of light enable us to do things like see through certain types of polymers or plastics, or get certain types of resistance to the effects of background light, or get good reflections from certain type, or remove the effects of pigments by going into the infrared. You get less of the influence of color, depending on what you're trying to do. But lighting is an area which has traditionally been, I think, neglected really in books on machine vision and in many courses, to be honest, in machine vision. But it's a very, very important aspect of the subject, because without proper lighting and effective lighting, we can't do any good machine vision work. Then talking about 3D machine vision, this is, I say, is a niche area we developed in our lab, because we got 2 really big areas in the Centre for Machine Vision, and that's 3D vision and deep learning. But with 3D, you get range data, and you get a deeper, more rich data set, which then you can use to solve all sorts of problems which are considered too difficult up to now to solve. This is an example of a camera that, 3D camera that Scorpion is supplying. I think they're using techniques such as binocular stereo, for example. So we'll feature various 3D vision systems that we can apply to a range of industrial components or products to demonstrate the benefits. And these benefits are really quite significant, because we find that by capturing 3D data, we can do things like segment objects of interest in the foreground and remove things that aren't of interest in the background, thereby simplify the image processing and make the system more likely to work in the real world. We can also make systems that are more robust in complicated situations. For example, we can go outdoors and still find we get functionality. And that's also something where deep learning comes in to help us. So it's really the combination of 3D and deep learning that gives us really advanced functionality that enables us to undertake tasks which have been considered too difficult up to now. Then photometric stereo is a technique we developed over many years in our lab and applied it to a wide range of applications in different sectors. It's where you have one camera and a set of lights in known positions. You turn one light on at a time and take an image each time. You combine that with a lighting model to get the 3D and 2D data from the scene. So to do this in our lab, we'll have sets of visible and near infrared LEDs and a camera and lens. And of course, we need some instrumentation for turning the lights on, because this has to happen at high speed so that there isn't a chance for things to move gently or change in between the shots being taken. And it's very good, we found, to take a robustly separating 3D and 2D data. So we use it for face recognition, plant analysis, and all sorts of other applications. And it works very well. You can do things like on tiles that are being inspected. You can detect whether you've got a molding defect or a printing defect on your tile. So there's all sorts of things you can do with that. Then going on to polarisation, this is another important technique where you can see here we've got a motor pulling a polarizer around and changing the polarization. So we can change polarization to get interesting 3D and other data from scenes. And to be honest with you, we've got a big project going on with the centre, composite centre, on inspecting composites during manufacture. We find that by combining photometric stereo and polarization, we can get really useful information on any defects that are occurring during manufacture and laydown of the composites. So this is an exciting project. We've built a new rig which combines both photometric stereo and polarization, and it does it quickly, automatically, so we can analyze components as they're being built. So this has got real world applications. Then the important final cell is, of course, AI, where we're showing how deep learning and AI, particularly convolutional neural networks, can solve real-world problems that have been considered too difficult up to now. So we see different objects in all different angles and different light conditions, and machine vision with deep learning gives us the power to recognize these objects, where up to now it would have been too difficult to do so. So we can do things outdoors, we can do it more complicated, and this might enable robots to undertake difficult, dangerous, and dirty tasks which have been considered too difficult to deal with up to now. So it's a really exciting long-term potential, really. So we'll have a cell rigged up with a camera and a lens, and of course a high-performance PC with a GPU, where we'll demonstrate the power of deep learning. So we'll be running possibly MATLAB with the deep learning toolbox, or Keras or TensorFlow, and maybe even Google Colab, where we can run it all online with the online GPU, which is quite exciting. So this will be an opportunity for students to tap into the exciting potential of deep learning. So the Scorpion Machine Vision Lab then, the BRL UWE, is enhancing CMV's ability to undertake the highest possible quality research and teaching in BRL UWE. We plan to build upon our past achievements in doing this. I think, if I say so myself, over the last 20 odd years, we built up a reasonable reputation for quality in the lab. We were entered, for example, with a significant contribution to the 2014 General Engineering Rep submission. And here, research quality was judged to be all of international standing, with 75% of it being world leading or internationally excellent in terms of originality, significance, and rigor. And that's on the internet, that information, if you want to look it up. And we were very gratified to get that rating, and we want to build upon that to take research in the BRL, machine vision research, and in UWE as far as we can, and for it to be as high quality as possible. So that's a little tour of what we're doing in the new machine vision lab in Z Block. So if you have any questions, or you've got maybe an industrial problem you'd like us to look at, do get in address, and I'm always checking. I'll get straight back to you. Meanwhile, I expect I'll see you around, and enjoy the rest of the day.
Thank you, Lyndon. That was very informative as ever. I'm going to go straight on, if that's okay, and introduce you to Paul Wilson from Scorpion Vision, who is going to talk through a little bit the company and the very, very appreciated sponsorship of the new Vision Lab that Lyndon's been talking about. So, Paul, I'll bring your slides up now and then over to you.
Thank you, Mark. Okay, thank you very much, Mark, and thank you, Lyndon, for that very interesting walkthrough of the lab. I was very pleased to be able to go and have a quick tour of it last week, and it really does look quite exciting. And the lab that we're sponsoring, it's quite extensive, a lot of room for workstations, and we're very happy to be sponsoring that and putting some hardware in there to help the students in their endeavours. I found it very interesting that, and Lyndon touched on this, is that often what is not really focused on very much is lighting, illumination, and optics, and so we can help with that. So I'm, as I say, I'm pleased to be able to contribute in that respect. And polarisation and different forms of optics and lighting is surely the foundation of building a really decent automation machine vision system. And our experience has shown that really, that's key to absolutely everything before you actually start, is to get your optics and lighting sorted out. So a little bit about us, a bit of background about us, who we are, and I'm going to show some examples of what we do, which I think you'll find quite interesting. Most of our work is in agriculture, so I've got a couple of agricultural applications to show you. Very, very, very intensive, very difficult work, but with the combination of the technologies that Lyndon has covered, we've been able to solve a lot of problems. So, who are we? We were established in 2004. I established the company myself. It was a channel to sell Scotland Vision software into the UK machine vision market. And here we are, quite a lot of years later on, with a well-established business, not just as a machine vision distributor of components and software, but also we build systems. We build systems in the high end, really. Most of our work we're using 3D machine vision. So that's where our main expertise is, and specifically in factory automation. That's where we work. It's mainly factory automation, and the key there is repeatability. We're looking for robust, high-performance systems that work with 99.99% repeatability if possible. And I said, most of our work's in food production. Majority of that food production work is actually agriculture. And I have some real-world examples for you. So the first one is a system we've only just recently completed. This is using a robot, and the system is actually being fed, or the camera's being fed in buckets, these lettuce which are placed upside down with the stem facing upwards. So if you picture that the lettuce has been harvested in the field, they go into a trailer, they go back to the pack house, and then they get processed. And the processing that takes place in this example is that they have to decore the lettuce to effectively separate the leaves out. I suppose it's really for mass market in catering, that kind of thing. So not the lettuce you buy at home, unless of course it's in packets, in which case that's where this product probably ends up, as well as when you buy your already trimmed lettuce. It comes from this process. So what's happening here is the lettuce are traveling under the camera at 1 lettuce per second, and the vision system has to locate the object in 3D. It's got to find certain features, and in this case it's looking for the stem. And what's very interesting is we're using a whole combination of technologies here that Lyndon referred to. We're using near-infrared, we're using stereo vision, and we're using polarized lighting, and we're also using an element of a convolutional neural network. We didn't start off using a neural network. We were trying to do everything in 3D, using feature matching and color analysis. But to get to the actual better than 96, 97, 98% repeatability that we wanted, with recognition of the stem in the right place, we had to use a convolutional neural network. So what happens is when the stem is recognized and its position in space is recognized, a robot end effector comes down and literally claws out the center of the lettuce. And it's very successful. It works really well. It's very fast. As I say, high repeatability and a great labor-saving system. So it can be used both with lettuce and other similarly shaped vegetables. So brassica in general, broccoli, other kinds of products like that. So that's an example of one of our 3D applications, and the system really is a conveyor belt, 3D camera, sensors to detect when the product's in place, and obviously a robot which is doing the final piece. Now moving on to something which is actually a lot older. This is a 5-year-old project, and as a contrast, this is actually a 2D system that is utilizing just color and texture analysis and shape, of course. And in this case, the sprouts are being trimmed, the end of the stem is being cut off, and what happens when you do that is the leaves fall away from the sprout, and effectively it's peeling the sprout. But in order to be able to do that, you need to really accurately locate the end of the stem. When we first started doing this, of course, we fell into the trap that, how difficult can it be to actually locate the stem on a sprout? Because let's face it, they're just the shape of a light bulb. Well, what we hadn't anticipated was that sprouts farmed in this country are actually not just farmed in this country, they're imported from other parts of the world. A lot of them come from Morocco. The ones from Morocco are they're just very, very round, like footballs. So the only way you can actually locate the stem on a football-shaped sprout is through texture matching and colour. Very challenging, took us a long time, took us several years to get this right. It was we could have used 3D on this, but we opted with 2D because there's a lot of investment in that in terms of what we do with the colour cameras. And also, what could have really shortened this project for us would have been using a convolutional neural network. That would have really accelerated progress on this particular project. So interesting, really, that how all these new technologies are becoming so important and really valid in terms of real-world applications. So with all that said, we know that lighting, camera technology, image acquisition is really important. It makes a massive difference before you even start developing a system. In the world that we're in, where our customers are expecting very, very high uptime, very high performance and high throughput, getting the image right in the first place is absolutely fundamental to what we do. So our contribution to the lab is that it's a combination of workstations with different camera types and imaging opportunities for students. We've got a combination of ring lights and dome lights and other forms of diffuse lighting, which we will build into the lab. One of our major lighting suppliers is a company in Germany that produce very cost-effective lighting. That's what we'll be using. And primarily the cameras we'll be using will be from HIC Robots, who are one of our main principals. And so we look forward to actually getting involved and helping the laboratory in its endeavours to improve education and get more machine vision engineers out here in the industry, because we really do need them. So it's a fantastic, exciting area to be in, and I look forward to seeing the output. So I hope that was not too fast. I hope that was interesting, but that's me. And please don't hesitate to contact me. And that's me over. Thank you.
That's brilliant. Thanks, Paul. Thanks, Lyndon. It was very interesting, especially the showing how, or talking about how difficult the problem of trimming, the Brussels sprouts is, when to a human we just take it for granted, don't we? That it's very straightforward. But I think machine vision is incredibly complex as soon as you start trying to do it in the wild. And you've really shown, especially the deep learning approaches, how much better it is. But I think what's really interesting about the facilities that we've been discussing and bringing this to the students is that they're going to get a hands-on feel for how difficult machine vision is, how much more difficult it is than you might expect. And I think that'll really, really, really benefit the students of the future, the engineers of the future, to appreciate just how much we take for granted. I see we've got a question that's just come in. Let me just bring it up. So this is from Jim Wormold. Is deep learning for machine vision as good as human vision? I.e., can autonomous vehicles see as well as human drivers? I don't know if either of you would like to hop on with your thoughts on that.
I think I'll defer to Lyndon on that.
Yeah, okay. Well, I think that deep learning is pretty good at getting as good as humans at something like face recognition, for example. When it comes to driving, again, we have many things in common between computers and humans, like binocular stereo for range, and then shape from shading for shape, and perspective and parallax and so on. But I think one big advantage that computer vision could have, or autonomous cars could have over humans, is it could be very highly multisensorial. So it could look beyond vision even to other types of like LiDAR or what other technologies it might want to use and employ them. So I think there's no reason why autonomous vehicles shouldn't be reaching a very high standard of competency, if you like, for automatic driving in the future. And that will be something to look forward to. The problem is, I think, that on the way there, you've got a bit of a mixture of humans trying to drive around and cars trying to do it. And if it was all automatic, it would probably be safe. But the dangerous part is when you're trying to move through that phase of partial automation. So I think, yeah, the answer is yeah, it could be as good as humans, if not better.
Brilliant.
Can I just say something on that from our limited experience with this, non-academics, although we have graduate engineers, but in the real world, with what we've done, working with organic products is quite difficult using classic machine vision tools to locate something, a feature that you're expecting it to conform to a particular shape and color. And whether you're talking about vegetables or whether you're talking about crustaceans, fish, they all take a different form. You can never guarantee that something is going to behave the way you expect it to. So with what we found with a neural network is that when you show it a training set, that your repeatability goes up from perhaps, what we're doing, from perhaps 80-90%. It shoots right up to well over 95% with a trained model, and that's something you've never been able to achieve using classic machine vision tools. So for us, it's a massive leap forward.
Yeah.
That's very interesting. It sounds like there's nothing that machine vision can't do, hopefully, in the near future. So I thank you both for your very interesting talks. I'll take you off and we'll move on to the next talk. So our next talk is from Kerstin Eder. She is a professor in computer science at the University of Bristol and set up the Energy Aware Computing Initiative. Her research is focused on specification, verification and analysis techniques which aim to help to design systems and verify the behavior in terms of the functional correctness and performance and energy efficiency. And it leads on very nicely from the last question that we had to do with autonomous vehicles, because she's going to talk to us about her research in the area of autonomous vehicle testing. So Kerstin, I'll hand over to you. If you've got some slides to share, I can bring them up on the screen.
Oh, I thought I had.
I can't. Yes, I can. They were just at the bottom. My mistake.
Okay, try again. Better?
Yes, perfect. Okay, I'll hand over to you.
Okay, thank you very much for the introduction. Hi, everyone, and welcome. As in the introduction mentioned, I am a professor of computer science at the University of Bristol, and I lead a research group that is called Trustworthy Systems Lab. And at the Bristol Robotics Lab, I lead the research team on verification and validation for safety in robots. And today I want to talk to you about our recent research activity on connected autonomous vehicles, in particular on the research on simulation-based verification. So the BRL has a number of exciting and really challenging research themes, and those marked in red, which is verification and validation and connected autonomous vehicles, have directly contributed to the COV research I'll be presenting today, and those marked in green are somewhat indirectly contributing to our COV research. Now, COV research at the BRL has quite a long history. You can see we started in 2015. In fact, researchers at the Robotics Lab have conducted COV research since the beginning of the funding provided by the UK government. The Ventura project was in the first round of innovative UK funding, and that was even before CCOV came to existence. And the Ventura project was amongst the first to get an autonomous vehicle on UK roads. There was also the Flourish project, which focused on the needs of older adults in terms of mobility, and also the Capri project, which recently finished, which provided a market-ready mobility service using trusted secure pods. There are several ongoing CAV projects, MultiCAV, RoboPilot, and CAV4th, and I was involved in Capri as well as RoboPilot. Now, what's important to realize is that the focus of these cross-disciplinary research projects has evolved over 6 years from investigations into user acceptability of individual CAVs to safety assurances and verification and validation for CAVs which interact with complex real-world environments. So today I want to focus mainly on the Capri project and the RoboPilot project. And they are very different in terms of their CAV application domains. Capri was focused on a pod in the Queen Elizabeth Olympic Park, and RoboPilot focuses on automatic delivery vehicles. So two quite different areas, but that gave us a really interesting opportunity to investigate the effectiveness of verification and validation techniques in these two different domains. So our research in both projects was focused on simulation-based verification, and in particular on advanced test generation techniques for verifying the safety of CAV development environments to help the CAV developers ensure that their vehicles meet the highest standards. So let's focus first on simulation-based verification. Now, there are a number of real big challenges in this area. There is complexity of the software as well as the hardware. And of course, in addition to this, we also have people and a really complex real-world environment. We're dealing with high levels of concurrency and temporal aspects. And as we all know, experiments are very expensive and potentially extremely unsafe. So at the BRL, we are investigating simulation-based techniques for testing CAVs, and we are using techniques that are well established in microelectronics design verification, and that is coverage-driven verification. Now, we're using those in order to verify code that controls robots, and that would be a completely different talk. But we're also trying to use these in order to verify autonomous vehicles. Now, I should say that my background is in microelectronics design verification. Bristol has a vibrant microelectronics design community, and they have been dealing with a lot of the challenges that we are facing here for several decades. And so it does make a lot of sense to learn from that community. And coverage-driven verification is one of the techniques that has been extremely successfully applied in that area. Now, to get to the starting point, we first have to have a lot of automation, and that means we have to have a test bench. Now, you can see the sort of test bench we have been developing, and let me talk you through this from the start. So, in order to verify an autonomous vehicle by simulation, of course, in the middle here, we have our simulator, and this simulator communicates through an interface with the vehicle control. Okay? So to set up our simulation, we start off with an experimental specification that contains all the environment and all the things we want to test in simulation. That gives us a particular experiment to set up, and there are two parts of such an experiment. One is the scenery, which gives us initial setup of the static elements for our simulation. And the other one is the dynamic part, the things that move, the actors. So that's other vehicles, pedestrians, traffic light, anything that changes state. And both of them we need in order to set up our simulation. We then also want to check whether the autonomous vehicle behaved correctly. And we do this by capturing a set of traffic rules and social norms as assertions, which then allows us to check these using assertion-based testing. And then, of course, we also want to know how thoroughly we have verified the vehicle. And that means we can collect coverage at different points. We can collect coverage in terms of the requirements, the scenarios, the variety of the different scenarios and their particular features. We can also collect coverage of the assertions that have been triggered during the simulation. And if we have access to it, we could also collect coverage of specific parts of the code of the vehicle and other coverage metrics that relate directly to the controllers that control the vehicle. Now, going into the details a little bit more on the test bench, this is how we generate a simulation environment. We effectively start from OpenStreetMap network data, which is annotated with OpenDrive information. We use a geospatial database for logging during the entire simulation run, and these log files are then used for assertion testing. The simulation is done either in Unreal Engine or Scala, and the logging is sufficiently detailed for assertion testing so that we can see when things have gone wrong or have nearly gone wrong. So this provides us with a CAV simulation environment into which we can integrate automated driving controllers from our project partners, in-house developed driving controllers, but also open source examples. And we can do this for a variety of different virtual environments, including, well, the motorway, bridges, normal road layouts, but also maybe quite unique road layouts, as you can see, this little double mini roundabout, which is quite challenging for human drivers as well. We can simulate this and we can check what the autonomous vehicle makes of such a situation. So there's actually quite a high fidelity simulation environment that we have built up. And this now allows me to go on to what we actually can do with this. And it does take quite a while to get to a starting point where you can do exciting and interesting novel research. So here we see an example of the database log that we can view. So on the right-hand side, we see a rather tricky scenario of an overtaking. So the red vehicle is overtaking the yellow vehicle. But the red vehicle is not doing this nicely, is actually cutting into the path of the yellow vehicle, forcing it to slow down. And you can see the detail that is being logged in the geospatial database down here. And this is the data that we then use for checking. And all this data is captured during the simulation. Okay, so now with this set up, we can do assertion checking. So we automatically capture when things have gone wrong. So in this case, our overtake and cut-in scenario, we have captured in an assertion the minimum distance that should always be observable between individual cars. And we have also captured other parts of the scenario. So there is a rich set of assertions available. And what you can see here is how a near miss is detected by our database. The simulator that we're using here is Scala, and we're using PostGIS and then SQL for the implementation of the assertion checking. Here is another example, a test case. We turn through traffic with and without a cyclist. So at the top, we've got a cyclist, which is shown right at the top here, but this cyclist basically just stops before the crossing, whilst at the bottom here, we have a cyclist that carries on and doesn't stop, which they shouldn't really. And this car should really be watching out for this cyclist. And as you can see, there is a collision. Now, these scenarios have been motivated by collaborations that we have had with colleagues in the Capri and Robopilot project in terms of accidentology. So looking at where accidents happen in the real world and then translating this into interesting scenarios that we can play in simulation and see what the autonomous vehicle makes of the situation. And this is how we detect the problem. So we have an assertion check that checks for collisions. And this assertion check actually captures here that an accident has happened and detects the collision quite nicely in this scenario. So with this test environment in place, we can simulate and monitor a given scenario, and we can also track all the actors in a scenario. But what about the actual generation of test stimulus? So we're exploring the use of artificial intelligence in test generation for autonomous vehicle testing. And in particular, I would like to highlight to you the work we have done on agency-directed testing. So agency-directed testing is a new testing paradigm. It's part of the family of model-based testing technique, test generation techniques, where we use artificial test agents to direct testing from what we would consider normal to edge cases. So on the right-hand side, what we see here is a scenario where we have shown as a red box an autonomous vehicle. And in front of this autonomous vehicle, we have two zones. The first one is the stopping zone. This is where a collision would be unavoidable. So we're not really interested in this because any agent that enters this stopping zone would cause an accident. What we're more interested in is whether entering this precondition zone here triggers the AV to stop or to change direction in order to avoid an accident. Okay, so the precondition zone is the target for our test agents. And in yellow, we can see test agents, in particular pedestrians. And what we'd like these to do is to walk along the path and then occasionally walk into this precondition zone. So we can train test agents to actively seek this sort of interesting, perhaps even critical situation. And we then have captured in assertions what makes a critical situation. And in particular, there is an assertion here that says, if there is any agent in this precondition zone, then watch out that the autonomous vehicle actually avoids that, because there is enough time for it to either brake or maneuver in order to avoid the accident. And so what you can see here at the bottom is the proximity agent that we have trained in simulation, in a Carla simulation. And these pedestrians are artificial agents that have been trained to do exactly what you have just observed. And we started off with this in what we call a grid world, where we basically show the autonomous vehicle as just a bar, very abstract. And we show the pedestrians again in yellow boxes. And there are different examples that we have run. We compare against different learning techniques, and the use of artificial agents for test generation is actually quite exciting and a really interesting area, and an area where we're using the AI in order to further automate the testing so that the rare events that we're seeking to challenge the autonomous vehicle with occur more often than they would normally occur because we can afford this in simulation. Okay, so what we're currently doing is we have now taken this a little bit further beyond the simple pedestrian scenario that I've just explained to you. And in order to do this, we have developed a gym environment for autonomous vehicles that provides us with a learning environment that is an adaptation of the OpenAI gym, specifically for joint action space and fast learning, and for multi-agent scenarios. So on the right-hand side, what you can see is the red vehicle, which is our autonomous vehicle. And the other vehicles are test vehicles. So these are the agents that we are training. So at the top, we see a bus stop. So the larger vehicle is a bus. And the lines show us what the autonomous vehicle can see or what is occluded from the autonomous vehicle. In the middle there, we can see a pedestrian crossing, where we basically have the red vehicle, which is the autonomous vehicle. And again, we have traffic, as well as pedestrians, and also lights, which we are controlling in the test environment. And you can, if you're participating in road traffic, you can probably think of lots and lots of different interesting scenarios where the combination of the oncoming traffic, the pedestrians, as well as the lights, make for interesting test scenarios. And at the bottom, we then have another example of a pedestrian crossing a road with one of our autonomous vehicles trying to avoid them. Now, with this, we can find rather complex test sequences because accidents don't usually happen from one action. They are a consequence of different things, usually sequences happening just at the wrong time together. And this also allows us to explore an innovative game theoretic approach to test generation. So if you want to become involved in this, we've got it all on GitHub, and you can download it and try it out yourself. Okay, so to sum up, we at the BRL have a strong presence in the CAF community. We are specialists now in simulation and simulation-based verification and A/B testing. Tony Pipe is leading the CAF research team, and I lead the verification and validation for safety in robots research team. But there is a number of other colleagues who are involved in the CAF project, or the several CAF projects we're running at the BRL. And feel free to contact any one of us if you're interested. Yes, and today we focused on verification and validation, in particular on functionality and safety. But there is also work that we're doing on security and trustworthiness, which unfortunately I haven't had the time to talk about today. Okay, so I'd like to thank you, and I'm excited to hear your questions.
Thank you, Kerstin. Excellent and very interesting talk, perfectly on time. So plenty of time for questions. If any of the audience have any questions, please type them into YouTube. In the meantime, I'd like to ask, you talked quite a lot about this, the sort of using AI to generate test cases, which is a really nice idea. I was wondering whether you might be able to flip it the other way and use that to help train the autonomous vehicles to be able to handle and adapt them, perhaps through some reinforcement learning.
Of course, of course. So while I focus on verification and validation in terms of, challenging the vehicle, you can also use this, and I think there is a lot of research out there that uses AI in order to train the controllers. Of course you can, yes.
Great, and we've got a question here from Rob, let's put it on the screen. He says that if the road network is effectively a chaotic system, can you ever fully design the vehicles to counter every potential risk? Or is it more likely we'll have autonomous vehicle-only infrastructure?
That's a really challenging question. Now, safety and security of systems is often not just achieved by making the systems safe, but also by designing the environment so that the overall system is safe. So it depends on where you draw the boundary for the system. And at the moment, as in the conclusion from the previous talk, the really critical thing is, and the tricky thing is, that we have conventional traffic and we're mixing that potentially with the autonomous vehicles, and that causes problems. So if you wanted it 100% safe, then I think you would have to look at something where you control not just the vehicle, but also the enclosing environment. And that's, yeah, very challenging to see how this could be translated into reality at the moment.
And following on from that, I suppose I've got a slightly different type of question. At the moment, it feels like we're very much in the Wild West of autonomous vehicles. You've got the Teslas and Audi doing really nice, quite automatic driving cars. But I assume they're developing them to their own safety standards, and obviously, you know, it's in their interest to make their vehicles as safe as possible. But do you think this should be handled at a government level and possibly an international government level to ensure that everyone follows the same sort of test procedures?
Oh, there is lots and lots of work on this. So there are already initiatives at the national level, at the European level, and at the international level in order to harmonize, standardize, and to sort of boost the development into a common direction, so that you know, we don't have this Wild West as you describe it. So there is a lot of work out there. Developers, governments, regulators. It effectively involves all the stakeholders, including consideration for ethics as well. So there is a lot of things that we need to answer, that we need to decide as a society, but also I know there's a lot of technical development going on, so that we at least pull on in the same direction together.
That's very reassuring to hear. The other thing that I find interesting is that there's some very well publicized failures of autonomous vehicles, specifically the Tesla type things, which in my view is a bit unfair, because obviously compared to the amount of human-based accidents that occur all the time and don't seem to get very much coverage, do they have this sort of really nicely adapted, you know, taking the tools from well-established techniques, for example, in microelectronics, like you do, and applying them? Do you feel that this is actually being done in a nice, logical way by Tesla and that sort of thing? And would that help avoid these sorts of collisions, or do you think that they are going to be similar to Rob's question, I suppose? Are there going to be too many test scenarios to be able to be entirely sure that things will be okay?
It's a really tricky question, and I think it's still a research question, in a sense that we realize if we were to do it all on the road, we would yeah, take a very, very long time to get there.
Yeah.
But even in simulation-based testing, you know, the reality gap is something that we have to deal with. So it's really tricky, and I don't think there is anyone out there at the moment who can for sure tell you what level of coverage and how much simulation and testing you should do in order for them to be happy to give you maybe type approval or the equivalent of type approval for the vehicle. I think there is currently research ongoing by the UK government to investigate how much you know, verification validation is required. So this is actually an open question that we are actively seeking an answer for.
Fantastic. Well, without sort of going too far into testing of non-deterministic systems that the wonders of AI is bringing us, I'm going to thank you, Kerstin, for a very interesting talk. And for all of our viewers, do feel free to contact Kerstin with any questions that you have at a later date. So once again, thank you.
Thank you.
Let's take you off the stream. So we're a little bit ahead of time at the moment. So I'm not sure if our next speaker is quite ready. I'm just going to, let me just see if he's there and ready. Mark, are you ready to start a little bit early?
I'm just waiting for one other person to come. I've got Arthur here, just waiting for one more, so probably 2 or 3 minutes.
Yeah, okay. So we'll just take a small break and be back in 5 minutes, and that'll get us back onto time again. Let me just put up the schedule.
What? Mark,
Okay. Hello.
can you hear us okay? Because we've had a bit of a microphone failure.
That's fine. I can hear you loud and clear. So, yeah.
We've got no presentations. It's just 3 of us having a conversation.
Perfect. That sounds very interesting. So I'll hand over to you then.
Okay.
So we've got Mark Corderoy and a couple of guest speakers as well to discuss an ecosystem for technology startups. Mark, if you'd like to take over the reins.
Thanks very much, Mark. Good afternoon, everyone. What we want to talk about this afternoon is the ecosystem that the Bristol Robotics Laboratory has helped create for startups, and how the university has sort of built upon that and created an enterprise zone, which is really quite unique in this area. I'm joined by two people who are running companies who've been through that ecosystem and are benefiting from it. So I will hand over to them in a minute and let them introduce themselves. My role in this is I look after the incubators and I provide that sort of help that some of these companies require. We work together on every aspect of business idea, markets, fundraising, pitch practice, everything like that. And maybe we'll cover some of those issues as we develop the conversation. But start off by introducing Arthur and Sam. Arthur, do you want to introduce yourself?
I can't hear Arthur at all, I'm afraid.
Okay.
Yeah.
My name is Arthur Keeling, and I'm one of the co-founders of Prof.
It's still very, very poor quality, unfortunately. It's fine if you look that way. I don't know if the microphone's there.
Hello, can you hear me?
I can hear you perfectly.
We had a microphone failure just before we started, so we're having to do a little bit of a make, do, and mend.
How about that? Is that any better?
That's perfect. Yep.
Okay, brilliant. Wonderful. Are you able to hear me now?
Perfectly. Yep. Loud and clear. Thank you.
What wonderful. Sorry about the technical issues. My name is Arthur Keeling, and I'm one of the co-founders of a company called Indus4, and we're currently based in Future Space, having left Launch Space, and we're developing an automation platform that helps companies access automation and enables them to benefit from those automation tools. But we've been on a journey through the incubator system here, and I started at UWE in the team entrepreneurship course and then left the university to join the incubator Launch Space here, where I started building the team and have since raised funds and now moved into Future Space, which is the commercial offices co-located with the space.
My name's Sam Ongbenu. I'm one of the co-founders of Altered Carbon. Now, Altered Carbon is attempting to digitize the sense of smell by creating a new set of electronic nose sensors, essentially. We started off in the Bristol, the BRL hardware incubator, and we've been there for a few years because it's got a diverse range of access to experienced technicians and academics, as well as giving us access to the machinery we need to develop this technology. We've been here, Altered Carbon's been running for about 3 years now, and throughout that, the BRL and UWE have kind of guided us and helped us throughout this entire journey to get to where we are now, where we're about to close our first funding round.
I will contribute from off camera. Just to give a bit of a scene setter then, we support about 85 companies within the enterprise zone. We have a number of incubators. We have the BRL hardware incubator.
Sorry, Mark, you're breaking up a lot again.
Is that any clearer?
Keep talking. It seems to be.
Okay. We have a hardware incubator which supports.
No. You're breaking up still.
I can't get much closer to the microphone, to be honest.
I don't know whether it's a very directional microphone like mine tends to be as well.
Yeah.
It's wireless.
Yeah.
The mic.
That's very good.
No, the microphone's not working. That's why we're having to run off the webcam.
That makes sense.
Can you hear me now, Mark?
Yeah. Yeah.
Okay.
Perfect.
So we have a number of incubators. A graduate
You've gone again.
Okay, I shall hand over to you to just ask you questions. So, talk through the ecosystem, and how the company.
I can start. So for Altered Carbon, one of the things that's really helped was, like I say, access to experts and academics. So with creating new sensors, there's a lot of things you've got to think about, whether it's how you produce the hardware, to how you process the signals, to how you kind of integrate it into new systems. And at every step of the way, they're difficult questions that take a lot of time to answer. And this is where UE, the experts in the BRL, have been really helpful here, where it comes to like developing new AI or ML systems for it, to testing out and kind of making sure that the hardware we're developing is also robust. So there, it's been really useful. But on top of that, being around similar companies that are in the at the same stage of growth or just a little bit below or above helps us to kind of avoid a lot of the pitfalls that typically befall companies at our age. So that is probably saved us hundreds of thousands of pounds already, just to if I was to put a number on it. And it really makes a difference being able to kind of bounce ideas off of other people as well.
Yeah, I think another really interesting dynamic of this space is the fact that you're based on the university campus. And what that enables is, one of the big challenges startups have is building that initial team and finding talent. We can't be competing with, Dyson and Google and people like that who are offering fantastic jobs. And so by working with the universities, which both run internship schemes from Bristol and UE, and both providing different sets of skills, which is really important as well. And we've been able to benefit as a company, and I'm sure you guys have as well, definitely, is in having interns come in who are incredibly bright and also sort of really eager to learn. And that's something, that sort of self-starting ability of those interns when they join. And we've had people who've joined as interns who have now become full employees of the company. And so we've seen that sort of journey within the ecosystem of students from courses ranging from mathematics to robotics, joining our company from both universities. And it's quite a nice collaboration and synergy of the two coming together, not just benefiting from the sort of academics who are here, who are sort of other paid professors, it's also the students around, which is really fantastic as well.
I definitely agree that the interns we've worked with over the past have helped us massively with different problems along the way. And I think it's really a mark of the university's skill at kind of getting students really engaged and prepared for the workforce. Because when they come in, it's not a difficulty to get them up to speed on what we're doing or how we work or our work ethic, essentially.
So talk me through the facilities you've got BRL, health, other faculties.
So the main facilities that we've worked with are the Health Tech Hub and the BRL and the Centre for Bioscience Research. We've done experiments with our sensors, which has given us an idea of what use cases we can use them in. On top of that, we've also been able to validate some of the underlying technology and do some deep dives into how our technology works by partnering and working together with these facilities, which made a really big difference for us.
We've worked as well with the Health Tech Hub, the RIF, which is the Robotics Innovation Facility, and we've worked with members of the BRL. And I think the key for us has been, as a startup, we can't go out and buy CNC equipment or some of the tooling that you need when you're working with some of these projects. And so by being able to collaborate and work with the university through schemes, in the Health Tech Hub, we were working on the vaccination program, and we've worked with the Health Tech Hub in that element. We've also worked with the Bristol Robotics Labs teams, whether it be access to additive manufacturing processes with 3D printing or metal work, and being able to get metal plates CNC to the requirements that we've got. It is an unbelievable facility to be able to be based here, because otherwise the alternative is huge capital expenditure for a startup, which isn't very viable, or going outside and finding companies. And that can sort of add lead times, which, you know, as a startup, you want to be moving really agilely, and it helps provide that support and, you know, access to technicians who, you know, you don't have to build as a team, and it's that sort of hardware equipment that you can't afford as a startup.
Yes, definitely. And it de-risks a lot of prior investment into certain areas. So we can, for example, with our experiments, we were able to test if our sensors could detect wound cultures, and by doing that, now we can now confidently pay more to go down that route. But if we hadn't done that test initially with the university, we probably wouldn't have been able to present this as a viable case going forward.
That's a really interesting point, and slightly, I think, leads on to, you mentioned earlier, investment that you've been doing. We have also successfully raised funding with the support of incubation managers. But I think that's a really interesting point of the capital that you've got to do and raise. Investors sometimes have a sort of a challenge not supporting hardware because they see it as that sort of capex. But actually, we've had support from incubation managers, whether it be going through our pitch decks, our financial models, and it's that opportunity to have someone to give you an eye over it. So it's not just the research and the students and the academics, it's also having access to business people who've been there before and are able to sort of sanity check any ideas or thinkings you've got on it as well.
The sanity check is a great way of putting it, because sometimes you'll have ideas about how the business will work or how the technology will work, and having someone experienced to bounce those ideas off of, to say, well, this sounds great, but in a practical sense, you have to look at this angle, really helps and streamlines the actual process of growing as a company.
And I think also we've had problems where, for a lot of companies here that are starting out, it's their first time. And when you get given a term sheet by an investor, you spend so long looking at these technical challenges of, you know, AI and ML, that suddenly you get a legal document, and that's another challenge that you've got to tackle. So the fact that the ecosystem here provides the sort of entire breadth, from the academics to someone who can help you look over a term sheet from an investor, is hugely valuable, and, you know, enables you as a company to move forward on so many different fronts as well.
Exactly. And they say hardware is inherently risky, but with the incubator's help, we've been massively able to de-risk a lot of those initial risks that investors were worried about in terms of developing the hardware. We can go to our investors and say, look, we have tested this hardware, we've validated it here, we've done this. Whereas if we were, let's say, on our own in the wild, there is no way we would have been able to do that just off our own backs.
I agree. I think the fact that you saying not being able to do it out in the wild is sort of a funny example, but actually we have had the same experience as a company, because our company has got a weird blend of software and hardware elements within it. So we have a platform, but also we've had to develop hardware alongside it. And that has meant we've had to invest the capital ourselves. But by working with, you know, partnerships with the RIF, which is a facility that helps companies investigate automation challenges, we've been able to de-risk that as well, which has been fantastic. Yeah. Indeed.
I'd like to point out this is a great giving a presentation.
Yeah, Mark, we can't quite hear you again, Mark. Whatever the hilarious joke was then. Sorry.
So fundraising process has been a journey. I think everyone can agree it is always going to be a journey, because it's where you start having to dot your I's and cross your T's when it comes to your business strategy. It's all well and good coming up with fantastic technology, but you also have to have the market and the use cases and the plan to actually reach your market as well. And that journey has been interesting, to say the least, but it's been a great growth experience as well. And I think that's one thing I really like about business in general, is that there are so many aspects to learn from, and fundraising is just another one of those, where dealing with investors, balancing what your investor wants with your vision for your company as well, and having the balance point of not being so rigid that you're never going to change, but also knowing why you have put your time and effort into your company is a very delicate art.
Indeed, and I think almost if you didn't have the support in the fundraising journey, you'd find yourself sort of, crossing your I's and dotting your T's the other way around. And if you didn't have that support, mistakes happen. But we've had, as a company, we've raised funds from angel investors. We've also raised funds through Innovate UK grants, which has then been supported as well by match funding. So we've had a range of funding elements come in. So each one has presented different challenges, and investors will demand one set of criteria from you, and grants will have another sort of impact on your business. And sometimes it's trying to strike that balance between the sort of administrative elements of grants versus investment capital, which is we found is much freer and we're able to move quickly with. But we have also found that we've been partnering with larger organizations, and we've actually been having a blend of not just going out and pitching fundraising from people. We've also been working with large organizations that have R&D spend that they're looking to do, and we're working with pharmaceutical companies to deliver some of our products. And they've been investing in us, and they've got the challenge of having, they've got a lot of cash, but they don't have the resources and time that they can dedicate to a challenge they'd like to tackle. And that's where we've been able to help companies address challenges. So we've been funding the company using private investment, grant funding, and collaboration with companies. And I think for us, having that blend has been a really strong support, because we've not been completely tied to a single
source, and it gives you the flexibility. I feel that's the one when it comes to fundraising in general. It's about being able to be flexible and maximizing. It's one of the good things about going from different sources, because they have their different requirements. You get to look at the problem from different angles. So, for example, the reason Innovate UK are so strict is because it's government money, but then the way they structure their projects is useful going forward for dealing with projects that have a lot of different stakeholders. Investors want you to have a 3-year plan or 5-year plan in reality, in reality a 3-year plan, but they say 5-year. And that gives you an idea of where you see your company in 5 years, and it helps you plan out like how you're going to grow as a company. And all of these are necessary parts that you always have to be considering as you're growing and as you're evolving as a company. So I think fundraising is always going to be a challenge, but it's always going to be, as long as we remain flexible, it won't be something that limits the company.
And we've had investments. So pre-COVID, there were pitching events run within this environment by different sections of the building. And that provides the opportunity as well to meet investors. And one of our angel investors came from one of those opportunities from the Bristol area. And by putting on those events, it allows you to have that practice of pitching, and you go through those moments, because we've definitely found that you have to pitch a number of times. And by having the space we're in here, you have the events, you have people you can pitch to, and it gives you that opportunity to practice it. And then hopefully you secure the investment. We were fortunate enough to, but I think without that support and ecosystem around you for the funding, it would be much harder.
I would definitely agree, because especially when it comes to pitching, it takes a long time to get it right, and you need to bounce off people, and it's nice to have that the layered stages with the pitching events that the BRL has set up. So when it comes to, like you say, having one-on-one sessions with people like Mark, to kind of having these events, having trial run events, and then having the real events, all of that gives you the confidence to speak about your business by the time when push comes to shove, I should say.
And interestingly, I think it nicely leads into the fact that because you're in a shared environment, there are other companies you can look to for inspiration who've been through the experience before. And examples of that would include Open Bionics, I think, is a very classic example of a company that was based here and has since left and gone out to other offices. But there's been a number of other startups that have been based within this space who've raised funds or done the stage you're just going through. And you're able to pitch to them as well, but also get their advice on your pitch deck or learn from their experiences as they're able to talk to you about whether something worked or didn't work. And actually, that ability to speak to other companies who've been through an experience like yours is invaluable. And 2 hours speaking to someone who's just been through an experience you're about to go through, you learn a lot more from. We found.
Well, 2 hours speaking to someone could save you 3 months' work, legitimately, just because a great example I would use is when we first started, when it came to budgeting. We had no idea how to budget properly. We spoke to a few companies who had been through the process, who had done it all, and they gave us so many tips and tricks on how to structure it, that it meant that instead of us spending, like I say, 3 months doing this plan, it took us a week or 2 weeks with working together with the people that we were speaking to. So it really makes a difference having experience and peers around you that you can share ideas and bounce ideas off of, and without the fear of your idea being stolen. Really and truly.
Yeah, absolutely. And I think also within a space like this, companies will learn a lot from their own failures, and when you are isolated away, you'll be making your own mistakes and you'll definitely be learning from them. But when you've got a large number of, as Mark mentioned at the beginning, over 80 companies based here being incubated, as everyone is making their own mistakes and trips and spills, you pick up learnings from them as well, as you see things happen which you then can avoid. And maybe you don't have to speak to them, you've just seen something happen, you go, oh, I've got to be very aware of that. And whether it be how someone's marketing a product, or how someone's done some particular outreach or spoken to a customer, or that they've had a bad experience with a customer, and you can learn from it if you haven't been initially interacting. And learning from each other's failures is almost as useful as seeing the successes.
If, in my opinion, more so. I feel like you learn more from failure than you ever do from success. So it's being able to have so many points of so many people around who are all going through the same journey as you, but just at different stages of this journey, is invaluable, really and truly.
No, definitely. And I think what's nice here as well is that ability to go from a supported incubator environment and then into sort of offices where you're paying rent, but there is support. So it's never just sort of flicking a switch moment for the company. It's about providing the stepping stones to go forward. And we've had that experience ourselves, where we have gone from a unpaid space where you're being incubated in an accelerated environment where it doesn't cost you anything, but that is the support that is provided. And then you grow out of it, and then you go into a small office initially, and again it's all done in steps, which doesn't kill the company off.
Definitely. And that actually goes back to the whole budgeting, because of the stages it goes in, you're very much allowed or given the space to learn how to budget well throughout your entire journey within the incubator, without it being, as Arthur says, being thrown into the deep end and just trying to figure out all the niggles that will inevitably trip up most young companies.
And I think the environment extends as well beyond just this initial sort of area on the campus that they've got here with UE Enterprise Zone. And you're able to have talks arranged where I know that Mark has arranged for people to come in and talk from external companies, and they're able to bring people in to do talks from the wider Bristol community as well. And Bristol's got a brilliant startup scene in it, and you're able to have these people come in and speak to you, and it exposes you to sort of the outside world of business. And as you sort of start to outgrow it, you start to see what's going on, and you're able to then connect with people in the wider area. And definitely. I think that's really useful support point here as well, is that access to the Bristol startup community, access to large companies, but also website designers, graphic designers. It's all out there in Bristol, and you're slowly able to access it from here.
I feel like the UEZ network is really wide, especially and really well established within Bristol. So almost when I speak to investors, when I speak to other business, let's say specialists outside of this space, they all speak highly of the UEZ and its network. So it just shows you how much is penetrated into the ecosystem.
Absolutely. I think it's because this, from our experiences, I'm speaking here personally, is that it provides a very unique incubation environment, whereas a lot of incubators will just provide you with a desk, and that's a laptop you can sit at and you can write code. You're provided access, as we've just mentioned, to the hardware, and it's sort of, there aren't many hardware incubators that will provide that support. So I think, it's a genuinely unique space to be, and there aren't sort of replicas of it. And, you can't go overseas and find a space that has this quite unique synergy of people.
I don't think, because we have been approached by various incubators, accelerators, and the like, and to date, I have not seen a incubator that has half the facilities and the support and the network that the BRL does.
No, indeed. So it's quite a diverse space to be.
Yeah,
absolutely.
I totally agree. But yeah.
Thanks, guys. That was really interesting. Can I just ask a quick question?
It's all good.
Can I just ask a quick question? With regards to the obviously great experience that you've had, is there, if I had a great idea for a product, what sort of technology readiness level would it need to be at for me to sort of benefit from being in the incubator? Is it sort of just a concept, or am I better off having something as a demonstrator, or does it not matter?
I mean, I think that it doesn't matter, and that you can come with anything from the classic napkin idea and a scribble and a concept, all the way through to potentially a working prototype. And they've got the facilities, but also the experience to take on ideas of the full range.
I definitely agree, but I will point out that the one thing, or the one prerequisite to business in general, is drive. So as long as you've got the motivation especially if it's just an idea to develop the team, and the BRL will help you with that as well. But the drive is required to be able to kind of take any idea from inception. But with the BRL, you can come with an idea at its inception. It could be a scribble on a paper, and there are people in here that can help you develop that idea into something real.
That's brilliant. Thanks so much. Really useful insights into the tech ecosystem, really. If any of our audience have got any questions or queries about how you can access these fantastic facilities, I guess get in contact with Mark Corderoy here, and he'll be able to direct you. So, Mark, do you want to just come on quickly and say anything or wave goodbye?
No, I just anyone who's got ideas, we're always happy to talk about ideas. We're always we understand these ideas are important to people, and as Sam said, if they've got the drive, we'll support them. And these two companies are a great sort of testament to what's possible. So thanks very much, guys.
No worries. Thank you very much for having us.
Thank you all.
Thank you very much.
Okay, so this brings us on to our final talk of the day. Some might say saving the best till last. This will be given by Dr. Gary Atkinson, who's a senior lecturer here in the Centre for Machine Vision, part of the Robotics lab. Gary, I think we'll be talking about his very innovative techniques for analysis using polarisation and how it applies to industry. But more importantly than that, I wouldn't be here if it wasn't for Gary, because he acted as my PhD supervisor about a decade ago. So welcome, Gary. I'll hand over to you. I'll just get your slides up on screen. And I shall hand over to you. Dr. Gary Atkinson.
Thanks for that, Mark. Everybody hear me okay?
Yep, loud and clear.
Okay, great. Yeah, thanks for that introduction. So, so Mark's right, I'll be talking about my polarisation work, but I'm going to kind of build up to that, not necessarily to big it up too much, because, but rather because I want to focus on computer vision more generally first in industry, and then talk about that as one of the exciting new developments that we've been working on here in the BRL. So I've broken down my talk into sort of two halves. The first half, will be a bit less than half here, is, I've called it the state of the affairs in computer vision. And I was going to call it state of the art, but that would have been far too ambitious to be doing that for a 20-minute talk. But it's just my personal interpretation of where we're at, broadly speaking, in the field, because it's quite exciting time. Everyone knows about how deep learning has taken over the field, but I think there's a lot of big developments that are being missed because of that. And you know, having worked in industry of late, I can also see the blend that's being put into computer vision techniques at the moment between modern and traditional methods. It's not like, you know, one theory's overtaken the other one method's overtaken the other one. It's about a blend when you actually go into industrial applications. And then I want to talk about what we've done here in the BRL. Some of my work, yeah, in particular, but I'm not just focused on my work. I want to talk about what we've done a little bit even historically, because I think that's quite useful to put it into the context of the current state of affairs. Hopefully you'll see what I mean as we work through this next 20 minutes. So I'm sure everybody knows what computer vision is, but I just double checked first. I will just give you, it's worth giving a definition. As far as I'm concerned, computer vision, I regard it as the opposite of computer graphics. Okay, that's kind of relevant to how we think about computer vision solutions, how we extract the data. This is the example I use for my students. Okay, if you wanted to render an image of a wooden box, for example, like that, what you would need in order to do that, you would need to know things like the coordinates of the box, the texture of the box. BRDF is all about how the box reflects light. You would need to know about the lighting conditions. And computer vision is basically doing the opposite of that. It's extracting information from an image. Admittedly, not a synthetic image, but it's, other than that, it's like the opposite of computer graphics. And one sort of insight I've like to just put forward is how I find actually quite remarkable. Yeah, in 2021, given all these applications I've just put on the screen, it's not quite a household term yet. I think if you stopped 100 people on the street and say, do you know what computer vision is? I think they would say, what? Computer what? Is that about how computers are going to develop in the next 20 years? So it's quite remarkable considering how ubiquitous it is in entertainment, medicine, you know, industry, where it came from, perhaps, all these things. It's massively widespread within our society these days. But interestingly, for this talk, I'm actually going to focus on computer vision industry, hence the title. Well, that's one of the first applications. I'm just going to go back in a way, not quite to where it all started, but certainly one of the first widespread applications was in industry. For example, on industrial inspection. I mean, Mark will know this picture well. This is one of our little bits of coursework that we set to our third year aerospace students using some software called Vision Builder that's designed by National Instruments. And this is like a halfway house between programming and a basic application where you can develop a simple script to inspect a component, in this case a rib component from an aircraft wing. And as I'm sure Mark will agree, you know, we go into the first tutorial of this for the students, and 15-20 minutes later they managed to produce something not too dissimilar to what I'm showing you now. That just shows you how robust some of these methods are for industrial inspection. And this is all using very, very traditional methods. And that's one of the sort of key features of this talk, as I said at the start. Just because computer vision is being taken over by deep learning, and there's so many talks you might listen to about that, I just want to make the point that we shouldn't forget some of these old useful techniques that we still use, especially in the industrial application. Not so much in, you know, driverless cars and things like that. But here's an example of one of the most basic algorithms in computer vision that you could possibly find. You take an image like this. It's an industrial inspection task, so it's under controlled illumination. And what we do is we just plot a histogram of the points, of the intensities. So this is the histogram. So we can see there's lots of dark pixels and then a bunch of bright pixels here. And we use a point in between the two to separate the background from the foreground, and we end up with this image here. Okay, incredibly simple method, but it's still used within computer vision, and within the industry. We still use techniques like that when that's adequate. And one of the important goals of this decade, I think you might say, in computer vision research is to work out where's the borderline between when we use these basic traditional methods like that and when we do something like use a YOLO CNN architecture, something like detecting these cars. This has become quite a famous image, I guess you might say, in computer vision these days. YOLO, if you're not familiar, you only look once. This is one of the deep learning architectures that's become very, very popular because it's incredibly fast. It's also incredibly reliable. And in this particular case, it's detecting cars. And the truth is that there's no traditional method that would be able to do that. Not that I'm aware of. I'm pretty sure that there is no traditional method that can do that with such accuracy. So somewhere between these two, we've got the boundary. And as I work through with you in a minute, some of the work that we've done, both of late and historically, that should become apparent, which areas of computer vision applications have started to rely on deep learning and which ones not so much. The other, perhaps one of the take-home messages from this talk, as I sort of alluded to earlier, is that this emphasis on deep learning, and don't get me wrong, I love deep learning. This is not an anti-deep learning book. But because there's been so much effort, a lot of the other things we've missed out on, especially when it comes to hardware. Traditionally, computer vision has focused on using monochrome cameras, RGB cameras, perhaps a bit more recently RGBD cameras, i.e. depth sensing cameras. And we've done this because perhaps these are the things that we use as humans. But there's other things that we can use. There's things like infrared cameras. Well, okay, they're still very popular. But hyperspectral cameras, where we break down the incoming light into the full spectrum, how the light is distributed through the wavelengths, not just spatially. Things like, as we said earlier, polarisation, which I'll talk about shortly. That is tapping into the polarisation state of incoming light in order to do something useful. And these are not obvious things for us as humans because our eyes aren't sensitive to them. Okay. Psychologists might disagree with some of that, but broadly speaking, we're not sensitive to the spectral distribution or the polarisation state of incoming light. But there's been big developments in these areas that I think perhaps a bit overlooked. So we're going to return to some of these points that I've just made as we then go through the second part of this talk, which is looking at the industrial applications of vision that we've worked on here in the BRL, both with deep learning and in using other methods. This image, for example, this is an image that's appeared on introductory talks about our Centre for Vision for many years, because it's one of the first things we do, but it's our interesting sort of starting point. And it's quite good to look back on some of this early work now to see how it would be different if we were trying to do a similar thing. The idea of this piece of work was simply to remotely measure the dimensions of these objects for packing, okay, for shipping purposes. And we used sequence of laser scanners and cameras. They're not as accurate as the ones available today, of course, but the principle's the same. And I think that's an area of computer vision that probably hasn't changed all that much during the past sort of 10, 20 years, other than the level of precision has increased. It's not been transformed by machine learning or anything like that. And then here's a related thing that we did many years ago to look for the shape of these aggregate particles, separate them into classes of, what did we call them? Angular, I think was the term we use, i.e. like very rugged looking samples versus smooth samples. And I think in this case, we would probably do that quite differently. I think these days we perhaps wouldn't use a laser scanner to classify the general appearance of something like that. We'd probably use a convolutional neural network and train it in sort of regressive mode to give a slightly arbitrary, you might say, value to indicate whether it's a nice smooth surface or a rough surface. The reason for doing that, by the way, is quite simply because if you want this in your garden, maybe you want them all smooth or you want them all rough or like that. Okay. If, on the other hand, we wanted to measure dimensions, which I think was part of this project as well, then various options. Maybe we'd still use lasers, but I think maybe we'd use deep learning for that as well. Now, this is an interesting example to talk about. This is a piece of work we did for an Indian company, automotive engineering company, which was to develop a non-contact wheel alignment system. And the computer vision component of this was to estimate, I'd like to say measure the orientation of the wheels on the surface. This is obviously just a test rig we used to measure the orientation of the wheels in sort of 2 degrees of freedom, which is quite difficult to do precisely, as we discovered at our expense at the time. But we applied a sort of laser scanning method. And I think that was the way to go. I think for this sort of application where you need a high precision measurement, again, I think the more traditional approaches for 3D scanning perhaps outweigh many of the machine learning methods that are becoming popular at the moment. But the next example, what we'll see is a good case of where both methods used together perhaps is the way forward. So this is some work that our ex-colleague Tim worked on for Autoglass, which you probably know Autoglass, the company that repair your windscreen, or repair and replace, as they like to say. And the idea here is what we wanted was, or what they wanted more than us, they wanted a system where you could take out a mobile phone after you've got a crack on your windscreen, take a picture of it, a picture of the crack lines, and then send it to them, and then they would decide what best action to take. And they've already got, obviously can't reveal the details of their methods, but they've already got a method that doesn't use machine learning or doesn't use deep learning to take measurements on these cracks. But the problems that we often face with computer vision, often they turn out to be some of the more mundane things. So you take an image of a windscreen with a crack in it. For me and you, it's pretty obvious what's the crack and what is something that you're looking at the other side of the windscreen or a piece of dust or something like that. But actually, from a computer vision point of view, that proves quite challenging because there's so many things that could be on the windscreen, the water, or dirt, or a leaf. Some things maybe could be mistaken for the crack if you don't have some sort of training method available. And also things that are the other side of the glass. If you imagine taking a picture from the outside, obviously the window's transparent, so you might see something on the seats or the steering wheel, something like that. So it's quite difficult to develop some heuristic or traditional computer vision algorithm that can separate all of these possibilities from a real crack. And for me, this is one of the perfect examples of where the modern approach to machine vision really takes its own, because you can just train up a massive convolutional neural network, or even not that massive, actually, probably in this case, to work out yourself, to work out more generally what a crack looks like, using methods that you can't possibly think about coding yourself, or you can't possibly think about some mathematical model that will separate a crack from all the other million things that it could be on the windscreen. But the deep learning method can do that no problem. Typical application, deep learning. And that's where, an example of where deep learning, it's just so far ahead of anything that we were doing until about 10, 15 years ago. Whether you then go on and use deep learning to measure the dimensions of the crack, or whether you use other methods, well, that's a debate. There's definitely ways that both could give results for that. And then projects that I worked on with Mark quite recently as well. Here's another example of where the more traditional methods, it's not quite industrial, the traditional methods, they struggle so much. This is an underfloor robot, as we call it, or survey bot, I should say, where we put it under the floorboards of a house. And what it's trying to do, as you can see on the right-hand image, is trying to spray insulation up onto the underfloor area to avoid heat loss and things like that, and drafts. But we don't want it to spray on pipes and things like that. So our part of this Innovate UK project is to embed a camera and then automatically detect floorboards, the walls, joists, and things like that, and segment the images. Here's some results. And again, all these features, they could look like so many different things, so many ways that a brick could appear in an image, that's where deep learning takes on its own really classical situation where I wouldn't even consider anything other than a deep learning approach. Now moving on to the polarization thing, this takes me to the point where, like I mentioned earlier, how we are overlooking perhaps certain features of light as they approach a camera or our eyes that could yield something quite useful. And let me just advertise, for want of a better word, polarization as one of those features that we might use. Okay. The light, as perhaps you know, is made up of an electromagnetic wave. So this is an idealized representation of that, where the blue vertical curve here represents a magnetic field in this case, and the electric one is shown in white. That's just for illustrative purposes. For the sake of a short presentation, let's just focus on the electric field for a minute. Now, most natural illumination is unpolarized in nature. So if we were to plot a similar graph, but just looking at the electric field of the light, rather than follow a nice smooth sine wave in a single plane like that, it would be constantly jumping all over the place. And if you did a thought experiment and you put your eye looking in the opposite direction towards the incoming light, you would see the electric field equally spread out in every direction across 260 degrees or 180 degrees. Okay. Now, of course, we can control that by passing the light through a polarizer. For example, you get in some good quality sunglasses, okay, in which case the light is then constrained to a single plane like this, and we call that completely polarized. But less well known is that light, when it's reflected from a surface, it will undergo a partial polarization process. Okay, so in other words, it would have electric field distributed in all directions, but it would have one preferred direction depending on the geometry of the reflectors. Now, I've used that for a few applications, but first of all, I should point out, so I'm just getting behind myself, before we talk about the applications, let's just think about how we measure that. Until recently, quite difficult to measure. The traditional method for doing so is you take a linear filter, like I've shown here, and you take lots of images as you gradually rotate the filter, and then a little bit of an algorithm gives you your angle here, the angle of polarization. So that's quite time consuming, but recently a few companies, most notably Sony, have started to manufacture what they call polarization camera, which mostly is the same as a standard monochrome camera, but on each pixel in the sensor, they've included a small wire grid polarized like this, as well as a microscopic array structure. Yeah, so this is like a face-on view, if you like. So you can see what they've got here. It's a bit like an RGB camera, but instead of having some pixels sensitive to red, some green, and some blue, they've got some pixels that have a vertical polarizer, some have got a polarizer at 45 degrees, and so on. And then a few very, very simple equations. I mean, very simple equations allow you to take the raw image from this camera and extract from that the polarization data. The polarization data consists of the principal angle of this electric field, as well as the ratio between the preferred direction of the electric field and the angle at 90 degrees to that. So in other words, is it completely polarized? Is it a lot polarized, or is it a little bit polarized in layman's terms? You can do useful things with that. So I did some work on that myself. This was before the camera came out, but using related idea to estimate some surface geometry. Okay, that's quite a big field of computer vision, has been for a long, long time, 3D shape estimation. I'll be honest, the quality of these results has been superseded by other hardware, other techniques, but it just shows you that it's a feature, it's a property of the light that we haven't used, but this at the very least proves that it contains some useful information for computer vision tasks. Some colleagues at University of Hiroshima in Japan, however, use it for an untapped area, and that is transparent surface reconstruction. So here we've got glass heart, and they use the polarization properties emerging from the heart to estimate its geometry. Obviously, the heart is the example, it doesn't have to be heart. And the reason this was so powerful is because whereas there are other methods in computer vision that will do things like animate a porcelain cat model, to do something with transparent objects, very, very challenging. And that's where polarization started to take on its own niche area. And then more recently, some of the work I've done is in another area that's been quite challenging for computer vision, and that's in carbon fiber inspection. So carbon fiber, if you're not from the industry, it's a material that is very, very strong, but also very lightweight. So it's good strength to weight ratio. And it consists of lots and lots of thin fibers like this embedded in what they call a matrix. I don't like the term matrix, but basically it's a resin of some sort to hold them in place. And you usually build up layer by layer your component. So the layer above this one, for example, would have the fibers at 90 degrees, for example, or something like that. The problem is twofold. Number one, if the fibers aren't lined up very well, then the strength of the component is massively compromised. And in particular, if you've got any gaps in the fibers, then it really, really is compromised. That's problem number one. Can't do much about that in computer vision. But problem number two is it's very difficult to inspect these things because carbon fiber surfaces, they tend to be black and shiny. And other than maybe transparent surfaces, black shiny surfaces, probably the most difficult type of surface that we come across in computer vision. And here's an example of an image on the right there. This is a standard intensity image, clearly difficult to do any inspection on that. But the fibers in the surface, they're made from carbon, a conductor. It's anisotropic because they're all aligned up with each other. So that actually means that the angle of polarization, or the phases I've called it here, when that is emerging towards camera, directed towards camera, the orientation of the polarization will have lined itself up with the orientation of the fibers in the component. So what I've done here is I've taken, I'm not sure if that's the same image or a very similar image, but taken it with a Sony polarization camera and extracted the polarization information in the form of the degree of the angle of polarization. And you can see now very clearly the structure of the fibers. So here, all the blue pixels have the fibers oriented horizontally, and all of the greeny yellow pixels are oriented vertically. Okay, so this is a woven material. And we can do things like plot a histogram of that. I've just shifted the axis a little bit so we can see it clearly. And you can see you get two nice peaks corresponding to the orientation, the most common orientations. And you can instantly do some global inspection on that data. For example, you could say, what's the separation of these two peaks? In this case, it should be 90 degrees to get best possible structural integrity. If it turns out to be 95 degrees, then clearly you've got some sort of manufacturing problem going on. There's inspecting components that's otherwise very, very difficult to inspect using machine vision methods. Here's just an example of three-dimensional components as well, just to show that we can get some information about those cases. So in this case, it's DOP is degree of polarization, and phase is the angle of the fibers. And then I think this is just about the final slide. Well, what I've got here again is showing how it doesn't mean that it doesn't mean that deep learning is still not useful, because we can detect now all the types of defects. Okay, what we've got here is a component. The reason it's green, that's just the way I'm encoding the polarization data. But this component here has got lots of defects on it that we've manually induced. And then we've trained up a CNN deep learning architecture to detect all the little defects in it. And that's something that we can do using a polarization image, but would be very challenging using the intensity image. In fact, you can see on the right here, this is the intensity image. So some of the defects come out clearly, but there's some defects here that you just can't see at all. But when we use the full information from polarization data and train up the CNN using that training data and then try and find new defects, it's much, much more reliable than using the standard image alone. So yeah, what I tried to do there was a few things in 20 minutes. Hopefully it wasn't too many things. I just tried to give you a bit of a flavour for my personal view of the state of affairs within computer vision and show how immensely powerful deep learning is, but also how sometimes we use more traditional methods, and also how deep learning, it can be improved by thinking still very carefully about the modality of the data and things like that, and using things like, in my case, polarization camera, in other people's case, hyperspectral camera. They can have big improvements upon the results we get for these industrial applications. Hope that was clear. I think I've got maybe 5 or 10 minutes. Is it 5 minutes for questions in case there's anything you'd like to ask me?
Thanks, Gary. That was really good. Very interesting, very thorough, and covered a huge amount of ground. And it's interesting seeing, the comparison of deep learning and traditional methods that you're using in the work. We've got a question here from Jim Wormold saying, will there be a return to traditional methods from deep learning? So I guess as we sort of moved and the world has embraced deep learning and that sort of stuff, especially in the vision world, do you think we might be going back to traditional methods?
No, I don't think we're going back to traditional methods. I don't think there's anything in the future at the moment that I can see that looks like it's going to overtake deep learning that you would call traditional. But I think my key message is that although we're not going back to traditional methods, there is still very much a place for them. And I think when it comes to industrial applications as opposed to academic research, I think it's about choosing the correct approach. And sometimes that will be traditional method with a standard monochrome camera, and sometimes that will be RGB data with a deep learning algorithm, and sometimes it might be a hyperspectral camera with or without deep learning. So it's about choosing the right tool for the job, really. I don't think it's about whether we're going to go back to traditional or whether we're in deep learning for good.
Okay, that's great. So there's no more questions coming in at the moment, but obviously feel free to contact Gary at a later date if you've got any burning questions, perhaps.
Yeah, I didn't put my email address on the screen. That's not a reflection of my desire not to receive any emails. It's simply Gary.Atkinson. It's very easy to remember. Gary.Atkinson@ue.ac.uk.
And I think all the contact details should be available on the BRL conference webpage as well, or contact anyone within the BRL. We can always help out. So once again, thanks very much, Gary. I'm going to take you off now.
No problem, thank you.
And that concludes a very diverse day of talks in this track. Thanks very much for watching. Thanks ever so much for all the questions asked and for the speakers keeping to time so excellently. Thanks very much. Please get in contact if you'd like to collaborate or just learn more about what we do here. Bye-bye.